Hello, everybody. My name is Beckwith, Paul Beckwith, and I'm an open book. At least that's what my hat says, open book. And what I want to talk to you today about is the Arctic Report Card version 2025. It came out just before Christmas. It generally comes out during the AGU, the American Geophysical Union conferences. And the first version of it 20 years ago in 2006 was just a print version that was passed out at the American Geophysical Union conference. And it basically covers the previous year of what's been happening in the Arctic. So it looks at all of the different things that are going on in the atmosphere, in the oceans, and on land, the permafrost, and the marine life and terrestrial life in that region, and how climate change is changing the equation and affecting everything. So today I attended the official release, if you like, Zoom on the Arctic Report Card, the presentation. So the actual report, I believe, came out for the AGU about 3 weeks ago or so, just at the end of last year. And I'm going to go into some detail about what the report actually says has been happening in the Arctic. So no blue ocean event yet. And that's the term I phrase for when there's less than 1 million square kilometers of sea ice in the Arctic. So we're still rapidly heading there. At the moment, the amplification, the Arctic temperature amplification is well underway, still continuing, and we're not seeing signs of cooling in the Arctic yet due to the slowdown of the AMOC. And I asked that specific question in the press release or in the Zoom call today, which is an hour-long presentation with some questions. Okay, so what can we say about the Arctic Report Card? Basically, it tracks the recent environmental changes relative to historical records, and this is the 20th year that the Arctic Report Card has been released, and it provides a clear view of the region that's warming far faster than the rest of the planet. So it talks about the state of Arctic's atmosphere, oceans, cryosphere, snow and ice, and tundra, and highlights the major transformations that are underway. And some of the highlights are the increasing Atlantification. So the Atlantic Ocean waters are impinging further and further into the Arctic. They bring warm, saltier waters northward. The boreal species are expanding northward in the Arctic ecosystems as the whole place is warming and the tundra thaws out. Rivers rusting is a fairly recent phenomenon over the last decade or two, where the active permafrost layer goes deeper and deeper and exposes different layers that are rich in iron and other metals, and those are mobilized. The water table drops, and the water that feeds many rivers goes through these pyrite layers, which releases sulfate and iron and other metals into the rivers, turning them red. Many of the rivers are turning red. Okay, so this is a good headline, sort of, 2025 Arctic-wide headlines. Record-setting temperatures. We had the warmest water year. Now they call it the water year. It goes from October 2024 to September 2025. So it includes a couple months in 2024 at the end of 2024, and it's valid up to September 2025. It gives them time to process the data and publish the report in December 2025. Extreme precipitation, highest annual amount for that year on record, the wettest spring on record in the Arctic. There's been large swings in the terrestrial snow cover in the Arctic. So the peak snowpack was well above average Arctic wide, And then, however, in June there was very rapid snow loss, so it set lows much lower than normal in June. And of course, this has huge effects on the albedo or reflectance of the Arctic. If there's much less snow cover over the land, then the darker land is exposed, therefore it absorbs more solar radiation, increasing the amplification of the Arctic region. Record low winter sea ice. So we had the lowest annual maximum extent of sea ice in the 47-year satellite record. That was in the maximum is in March. We had lower than average primary productivity in a couple of regions, but overall in general, the productivity was higher as the Arctic is warming and there's less sea ice. There's more productivity, more chlorophyll A, more phytoplankton in the oceans, and more greening of the tundra regions, the permafrost regions that thaw, and then they allow a lot of growth. So we had record high tundra greenness observed across North America, record temperatures in the fall, autumn in 2024 that persisted into winter 2025 in the Canadian Arctic archipelago. We had very dry conditions, a bit lower latitudes in Canada, so there were lots of forest fires. Greenland temperatures were above average in the spring. There were records at the peak of the ice at Summit Station in May. Summer temperatures overall close to average, but there were months that were much warmer. Glacial thinning, warmest on record in Arctic Scandinavia and Svalbard. Warmest sea surface temperatures on record in the Kara Sea up in this region off Russia. Record low sea ice extent in May in the Laptev Sea over here. Near record low sea ice extent in February and March in the Bering Sea and Sea of Okhotsk. So all of these things happened. Yeah, so this is the website for the Arctic report card. And if you look at I just remember that this is the 20th version of the report. This report goes back 20 years. Tracks rapid Arctic warming and change. So this is there's an archive that you can access. So we'll look at the archive in a minute. But first of all, these are the headlines for 2025. So surface air temperatures across the Arctic from October 2024 through September 2025 were the warmest on record since 1900. In the autumn of 2024, winter of 2025 was especially warm across the Arctic, and I'll look at the data, with temperatures ranking first in autumn 2024 and second in winter 2025. The last 10 years are the 10 warmest years on record in the Arctic. Since 2006, the Arctic annual temperatures increased at more than double the global rate of temperature changes, and we'll look at how the temperatures change in each of the seasons. The precipitation from October 2024 to September 2025, it set a new record high. So it's getting wetter and wetter and wetter in the Arctic, more and more precipitation, more snowfall, more rainfall. The precipitation totals for winter, spring, and autumn were among the top 5 since 1950. The records haven't gone back for precipitation much further than that. In the ocean, in March 2025, Arctic winter sea ice reached the lowest annual maximum extent in the 47-year satellite record. So when there's less Arctic sea ice at the beginning of the melt season, then the risk of a blue ocean event gets ever higher. September 2025, with minimum ice extent, it was the 10th lowest minimum sea ice extent. All of the 19 lowest September minimum ice extents have occurred in the last 19 years. In August 2025, the marginal seas of the Arctic Ocean's Atlantic sector, so the division between the Arctic and Atlantic, the average sea surface temperatures were 7 degrees Celsius or 13 Fahrenheit warmer than the 1991 to 2020 August average. So a recent average, the climatology, much, much warmer in 2025. The oldest, thickest Arctic sea ice, which is over 4 years old, as defined as over 4-year-old ice, it's declined more than 95% since the 80s. The old thick Arctic sea ice, the really tough stuff, is vanishing. Multi-year sea ice is now largely confined to the area north of Greenland and the Canadian archipelago. Other regions, it's just disappearing. The Arctic Ocean regions that are ice-free in August have warmed by 2.3 Fahrenheit since '82. From 2003 to 2025, the phytoplankton productivity spiked 80% in the Eurasian Arctic, 34% in the Barents Sea, 27% in Hudson's Bay. So with less and less sea ice, there's more penetration of light into the ocean. The nutrients are there, so you get phytoplankton productivity going way, way up, and therefore you get zooplankton going up, and then the food chain responds accordingly. The plankton productivity in 2025 was higher than the 2003 to 2022 average in 8 of 9 regions that were looked at across the Arctic, so it's widespread. Atlantification, the influx of water properties from lower latitudes, fresher water coming up. It's reached the central Arctic Ocean. Well, not necessarily fresher water coming up, but warmer water coming up from the Atlantic. It's reached the central Arctic Ocean, hundreds of miles from the former edge of the Atlantic Ocean, so it's penetrating deeply within, changing the vertical properties of the water column, and therefore causing more and more mixing and churning, and therefore less and less sea ice. It's a vicious feedback effect. The Atlantification weakens the Arctic Ocean's layering of water, like the halocline moves up to the surface. You know, that's the salt boundary, which separates colder, salty water below from fresher, less salty water above. So that halocline is vanishing at times. So there's more and more mixing. So there's more heat transfer of water, warmer water from below in some cases, melts the sea ice, threatens the ocean circulation, the overall thermohaline circulation pattern. The warming bottom waters, declining sea ice, and rising chlorophyll in the Chukchi and northern Bering Seas are driving shifts in midwater and bottom-dwelling species, so it's reshaping fisheries, Arctic food security, indigenous subsistence practices. Now, on land, the glaciers in Arctic Scandinavia and Svalbard had the largest annual net loss of ice on record between 2023 and 2024. So those glaciers are being slaughtered, basically. The Greenland ice sheet lost an estimated 129 billion tons of ice in 2025. That's less than the annual average in the recent decades of 219 billion tons per year between 2003 and 2024, so it's less. But it's continuing the long-term trend of net loss. Alaskan glaciers have lost an average of 125 vertical feet, 38 meters of vertical feet of ice lost since the mid-20th century. So that dramatically lowers the ice surfaces statewide, the volume of ice, the water stored in the ice. The ongoing glacier loss is contributing to steadily rising global sea levels, threatens Arctic communities' water supplies, it's driving destructive floods, increasing landslide and tsunami hazards along coastlines, and also threatening infrastructure. Throughout the Arctic, the snowpack, so snow on land, it was higher than normal during the 2025 snow season. So that means that it's higher than normal, of course, on the sea ice as well. It remained high through May, but in June it dropped off a cliff. Snow cover extent dropped below normal, consistent with levels in the past 15 years. The June snow cover extent over the Arctic today, it's half of what it was 6 decades ago. So the Arctic is getting a lot darker. It's becoming a lot darker with lack of this snow cover. In over 200 Arctic Alaska watersheds, iron and other elements released by thawing permafrost, it's turned pristine rivers and streams orange, okay, from over the past decade. It's like iron oxide, rust, is infiltrating many Arctic watersheds. And I already talked about why, because the active layer is thickening, so the water's getting down to the pyrite deposits, and then it erodes away the pyrite and turns the rivers red. These rusting rivers the acidity it's much more acidic, There's elevated levels of toxic metals, so the water quality is degraded. It compromises aquatic habitats and erodes biodiversity. It's also, when this water gets into the ocean, it contributes to the phytoplankton blooms, right? Because iron is a key nutrient for phytoplankton. The causes of the rusting rivers and impacts to rural drinking water and fisheries is being studied. The greening of the Arctic is ongoing, is far-reaching, first detected in the late 1990s. It's changed the permafrost. As it thaws and there's more water, surface water, there's more greening, there's more growth of shrubs and trees and small bushes and stuff going up to, you know, huge whole forests are appearing in a matter of years after the permafrost is thawing. Huge implications for global climate and the carbon cycle. The maximum Arctic tundra greenness, it was the third highest in the 26-year satellite record. So it had near record high values since 2020. The trend has continued. There's an Indigenous Sentinels network that's trying to monitor and observe what's happening with weather, wildlife, and environmental change in the Arctic. That's been continuing for 20 years. Great data. And on St. Paul Island, Alaska, there was a food security project and a new research center that's looking at different seals and different animals and contaminants of mercury and so on. So there's all of these things. So it's a very comprehensive report. The archive, like I said, it goes back to 2006. And you can download any of these reports. And you can get the older ones. You can get the reports going back to 2006. And I thought it was interesting that here, you know, they talk about what's being talked about in each of the reports from the first ones to the latter ones, and you can see what's being focused on in different reports. And you know, they go into detail here, and also there's I think you can see what are some of the key topics, like each one covers special issues as well. Okay, they're all different. So the rusty rivers in Alaska is a key feature of this present report. And then you can look at the from the home page, you can just look at the indicators. So if I go back, so this is the page that I showed you where you can download the report, which I'll show you in a minute. And I'm just looking at the report card data dashboard. That's what I selected here. So you can look at the different parameters, and it gives you key takeaways. So this is the Arctic annual surface air temperature, for example. And you can, you know, scroll over to get the data. The blue here, this is global annual surface air temperature, and this is the Arctic temperature. So you can see how this slope is much higher. Arctic temperatures are rising much faster. This is Arctic temperature amplification. The Arctic's warming at least 3 to 5 times faster than the rest of the planet. On average, they say it's about 3 now. For years, people, they'd stick to 2 times, but then they finally got realistic and say 3 times, but now it's actually even higher than that. Depends on the latitude. So you can look at some of the data, for example, on precipitation in the Arctic, the rate of change plus 0.75% per decade increase in precipitation. That's annually. You can look at terrestrial snow cover and see, like, so June snow cover extent declined at 8.7% per decade. May declined at 2.5% per decade. So this is the May snow cover decline, and this is June, and there's more variability in the June numbers. You can see that. Greenland ice sheet, ice loss, 219 gigatons per year is the recent rate. Sea ice extent, the sea ice extent, this is in March, the maximum. So we had the lowest maximum sea ice extent in 2025, 14.12. This is a million square kilometers, so 14.12, and the minimum's hovering, you know, the minimum year here, 3.57 in 2012, which we haven't matched yet, but the trend is still downward. You can look at the trend. Maybe a slowing AMOC is maybe the things would be taking off a lot quicker if the AMOC wasn't slowing down. I asked that specific question during the press conference. Sea surface temperature, 0.82 Celsius above the 1991 to 2010 climatological mean. This is in August. Look at the sea surface temperatures continuing to rise up. This is 2007, was very warm, but the trend is upwards. Ocean primary productivity increasing significantly. Look at this, the rate of change, 21.6 teragrams of carbon per year. That's the annual rate of change, 2003 to 2025. So look at this curve, looks exponentially going up. The ocean is getting a lot more productive because of the lack of sea ice, more sunlight penetrating. And then tundra greenness, and you can just hover over and you can see, so this is over Eurasia, this is circum-Arctic, different data sets and so on. You can see the rise of the greening. The NDVI, which marks greenness of the region, it's increasing 0.013 units per decade, the NDVI. So this is a good source of quick data. And then we've got the report card. Okay, so I'll go into some of the details of the report card without making this video too long. And the last thing I wanted to show is, this is at St. Paul Island, where they did specific studies on, and look where it is. We've got Alaska and the archipelago here, and it's smack center in here. So it's very isolated. I think 400 to 500 people are on it. There's an airstrip. There's a scientific base there now, and they're doing lots of research in the Arctic. So this is a report card. Like I say, 20 years of tracking rapid Arctic warming and change. Lots of good images and stuff. Lots of groups involved. Very, very rapid publication. It talks about all those different areas, some of which I've touched on. I talked about the headlines, sort of, what's happened in the air, in the ocean, on land. So I've talked about that. So let's have a look at some of the technical reports that are in here. So this is good. This is like an executive summary. It shows some of the vital signs and trends. The autumn and winter Arctic temperatures are increasing twice as fast as the globe since 2006. August mean sea surface temperature north of 65 degrees north, increasing 0.3 Celsius per decade. Takes a lot of heat to warm up water, as you know. 19th lowest September sea ice extent in satellite record, all within the last 19 years. Arctic annual net primary production increased by 30.5% since 2003. So in 2 decades, we've got a third increase in ocean primary productivity in the Arctic. And a big part of that is due to declining sea ice, more sunlight's going into the ocean, the nutrients are there, so you get huge proliferation of phytoplankton. And so we're getting huge primary productivity in the ocean and also a greening of the tundra. The annual maximum tundra greenness is increasing across most of the Arctic. That's the case since '82. Greenland ice sheet net loss has occurred every year since the late 1990s. Terrestrial snow cover really high in the winter, but in the June snow cover extent reduced by 50% since 1967, and it dropped significantly this last year as well. Precipitation trend increasing in every season since 1950. The greatest increase of precipitation is in the winter, more and more snow. And then this is, I showed you, I went through this image of the globe and talked about the different things in there. Okay, so let's go to the specific sections now. This is interesting. These are different ecological events that are chronicled. So if you want to know about declining caribou, 2008, they had a huge article on it. Arctic char, 2010. Wildfire, high latitude wildfires, 2017. algae blooms, whales. So rusting rivers, degrading water quality this year. Arctic tundra is transitions to being a carbon source from a carbon sink, and so on. So you can look at specific things in these different years. All these reports are available online. Okay, so surface air temperature. So let's just have a look at some of the headlines. Dating back to 1900, the Arctic had the warmest water year. The water year is just that month range, right? It's not January through December because of the timing of when the report's released. It's always from October to September. That's for all the data sets. So the warmest water year and the warmest autumn on record. Since 2006, Arctic autumn and winter air temperatures have each increased by more than twice the increases in global air temperatures. And that's cascading to increasing glacier melt, sea ice decline, greening landscapes, and other ecological changes. So the data sets are here. Now this is from 1900 to present day. The last 20 years that's what the dashed line is, and this is annual, and this is global air temp. Global is the blue, and then Arctic is the red. So annually. So it's increasing on an annual basis much faster than the global average, and there's a huge seasonal difference. So this is the autumn. Look at the warming in the Arctic compared to the global. Huge change, 0.77 degrees Celsius per decade in the Arctic, 0.33 in the globe. This is in the winter. 0.87 degrees Celsius per decade. Look at the spikes up here. More than double the global change. And it's there's hardly any difference in the summer. So the Arctic warming in the summer, it's about the same rate as the global average, 0.32, 0.31. And it's slightly higher in the spring. And then so the spring is slightly higher. Then in the summer, it's the same. Then in the autumn, you get a big increase of warming in the Arctic compared to the globe. And then in the winter, that carries through. And it's even larger increase. So it's interesting to see the changes. You can see the distribution of the warming. This is autumn 2024. The red areas are surface air temperature anomalies. These are differences from the mean, the climatological mean. Approaching 6 degrees Celsius warmer in these regions. This is in winter, this is in spring, and in summer it's much reduced, okay, and as I mentioned already. So you can see the geographical distribution in the Arctic, and then there's also, this is sea level pressures, which indicate air densities and things, so the colder areas, the warmer areas, and so on in the different seasons. Okay, so all the data is there. You can look at it. This is open source. I'll give in this report. Okay, precipitation. So we've already said precipitation averaged across the Arctic for the water year 2024 to 2025. So that's October 2024 to September 2025. Record high. Winter, spring, and autumn were each in the top 5 highest. So the summer was unusually dry over parts of Eurasia and Canada. The intensifying water cycle with more extreme precipitation events, it threatens to further disrupt the ecosystems. And we're getting these extreme precipitation events at lower latitudes too, as you can attest to and have experienced if you live in large parts, in parts of North America that have been hammered in the last week by storms and so on. And I'll do a separate video on that, I guess. So you can see the distribution of the precipitation. So much rainier, much more precipitation, much drier is the brown. In autumn, in winter, in spring, and in summer. The anomalies and then heavy precipitation events. We're getting much more of these RX5 precipitation events, which is the maximum 5-day events in each season. So we're getting, and these areas here, the wettest, the dark green, are the wettest on record up here in these regions in autumn, winter, spring, and summer. So we're getting a much wetter Arctic. than we had before. And this shows you a couple different data sets for the amount of precipitation, the percent of the average. So increasing in, look at the winter increase is much larger. So it breaks it down into the different seasons. And this is the annual precipitation trend, centimeters per year. And you can see the areas that are getting a lot more precipitation than normal. And also, so there's a lot less sea ice. So therefore, there's a lot more exposed water. Therefore, there's a lot more evaporation. There's a lot more water in the atmosphere. And not surprisingly, there's a lot more precipitation, right? It's just logic 101. Terrestrial snow cover. So the snowpack at the peak of the snow season, it was higher than normal over much of the Arctic. It remained high through May, and then it just collapsed in June. So June snow cover extent dropped below normal, and that's been happening typically over the past 15 years. The June snow cover extent over the Arctic today, it's half of what it was 6 decades ago. So that's a lot more exposed land. It's a lot darker Arctic. It's a lot more temperature amplification. More light is being absorbed at the surface than was previously. So the loss of snow cover directly contributes to amplified warming in the Arctic. It affects permafrost deterioration, timing of freshwater availability, ecosystem health. So not only does the permafrost thaw, but you get a greening of the Arctic, and that green material absorbs a lot of sunlight, contributing to the warming as well. So this is some of the snow cover extent anomalies in May over the years. And in June, the drop is much larger in June. And here's where we were over the Eurasian Arctic and over the North American Arctic in June of 2025. And you can see this is the anomaly in 2025. The line, so much lower than, and this is the historical average. Recent average is here, and it's much lower. Okay, so snow cover duration anomalies they give on the land with much reduced snow cover. This is the rank, April. In April there was quite a bit of snow cover, right? So it all vanished over as the Arctic started to warm. So they talk about the stats and how they collect the data and stuff. Greenland ice sheet, I've already mentioned the mass balance, minus 129 gigatons. The 2003 to 2024 annual average, minus 219. So it's slowing down here. So is this from the AMOC? The jury's out, remains to be seen. Need more data. This is the drop here, mass in gigatons of Greenland, and these are the GRACE satellites constellation with recent data, IceSat data, so different data sets showing the change of the Greenland, the mass loss, and there's different snowfall accumulation measurements. Like I said, the snowfall's up. So the snowfall up is going to perhaps reduce the mass loss. These are different, this is mass balances of different regions on Greenland. So most of the stations are on the coast. And you can see this is summer, autumn. So June, July, August, September, October, November, December, January, February, March, April, May. And then the anomaly, the mass balance year, temperature anomaly over that region, right? Warmer temperatures, more surface melt. The redder, the higher the temperature. So this region, 3 of the months were red, and you can see the different stations and where most of the highest melt is occurring. So lots of granular data. This is the surface melt, and this is 2025, the blue. And you can see the large variation and fluctuation. This is melt day anomalies. The red is the highest. And then solid ice discharge. Okay, so that's Greenland ice. I'll move on. Okay, sea ice, right? This is very important. had the lowest annual Arctic maximum extent in the 47-year satellite record in March 2025, but the minimum was only the 10th lowest. And the last 20 years we had lower extent, younger and thinner ice cover. So we can have a look at so there's more marine traffic in the Arctic. So we can have a look at, this is the concentration anomaly. So blue is, there's much less ice concentration. This is in March at the maximum, and this is in September at the minimum. So all of this ice was lost essentially in all of these dark blue regions. So very little sea ice. And this is what 2025 did. So in the points where there's maximum sea ice, we were setting record lows, and then here we are back in the envelope, so you can see compare it to maximums, previous minimums, and so on. Okay, so lots of data on the sea ice, and this is the melt onset dates. When the ice started to melt, the anomalies, sea ice age. This is very interesting. So in 85, look at all this yellow. This was old sea ice, old, thick, hard sea ice, which there's almost nothing of now at the moment. So this is a 2025 distribution. All of this was ice that was 0 to 1 year old, and then some 1 to 2 year old, 2 to 3 year old, 3 to 4 year old. But the yellow is all pushed up against the Canadian archipelago. So when we have a blue ocean event and less than 1 million square kilometers, it stands to reason that this whole region will be clear of ice. The only remaining ice will be stuck just north of the Canadian archipelago. I think that's pretty clear. So the blue ocean event will just have sea ice just stuck to the north of the Canadian archipelago, gone in the rest of the Arctic. So will the AMOC hold together to allow this to happen, or will the AMOC slow down enough to reverse these sort of trends? Okay, that's a big, huge question in climate science. And I'll have to try to figure out what I think is going to happen. So you can ask me what's going to happen. I'll have to think about that more. This is in April 2025, sea ice thickness. So some 4 meter, down to no ice. 0 to 1 meter is the darkest regions, and that's down in Hudson's Bay and, in the Straits here and so on. And then this is the anomaly. So red areas are, minus a meter anomaly. Blue areas are thicker. And then it divides up the different regions of the Arctic as such and looks at the anomalies from 2011 to 2021 in this table. So lots of specific detailed information on that region. Sea surface temperature. In the marginal seas of the Arctic Ocean's Atlantic sector, August 2025, the mean sea surface temperature anomalies were as much as 7 Celsius warmer than the 1991 to 2020. This is a climatological mean. This is a recent mean. It's not 7 degrees, so it's exploding even compared to recent averages. There were some anomalously cool August sea surface temperatures, 1 to 2 degrees cooler in parts of the marginal seas in the Atlantic Ocean's Pacific sector. The August mean shows warming trends, especially in regions that are ice-free now in August. Mean sea surface temperature increases 0.3 degrees Celsius per decade in the region north of 65 degrees north latitude. Okay, so we can see what the sea surface temperatures did. These are the different descriptions of the different ocean basins in the Arctic. This is sea surface temperature in August 2025 relative to 1982 to 2025. This is sea surface temperature, degrees Celsius, here. And this is the relative to the climatological average, 1991 to 2020. You can see these areas were very, very warm sea surface temperatures. So the ice left, and then the seas warmed up a lot in those regions. The percentile rank, right? So the red areas are the warmest, and then it compares what happened in 2025 to 2024. So, and there's more sea surface temperature anomalies here in some different months. So June, July, and August. So you can see, as the sea ice extent is disappearing, the marginal seas around are getting warmer and warmer and warmer. No surprise there. This is a trend, the linear trend of sea surface temperature warming. And then there's trends here from 1982 onwards in different, the Kara Sea, Laptev Sea, Barents Sea, and Chukchi Sea. So Kara Sea looks like it's warming the most. And again, you can go back to this diagram here. So up in this region, the Kara Sea is warming the most. That's in these regions here that are the reddest. Okay, so the data is all there depicted in multiple ways. Okay, so let's move on. Arctic Ocean primary productivity, right? There's more and more marine algae as we get sea ice decline and the water gets warmer, and there's plenty of nutrients. So you can see I'll just show you some of the charts here. So May, June, July, August, and the percentage of average, so much higher than average, and the darker the green, the more biological activity, chlorophyll A, which is from the phytoplankton. So, as we lose sea ice, as the water's warming, you get more and more phytoplankton forming in the seas of those regions. This is some of the sea ice concentration anomalies, so you can match the phytoplankton blooms from where the sea ice anomalies are the largest. Okay, no surprise there. Mean annual primary productivity, and then the trends in grams of carbon per square meter per year per decade. That's measuring the concentrations of chlorophyll of phytoplankton, and you can see that where the seas are warming and the sea ice is disappearing, you get the highest anomalies. This is so this is annual primary productivity. How is this different? Mean annual primary productivity, so A and C, maybe you have to read this. Oh, this is March to September only, and then this is for the other months, I guess, for the full year. Okay. Anyway, devil's in the details, right? This is primary productivity, grams of carbon per square meter of area per year in the various regions. So in all of the various regions. Okay, so we're getting a greening, we're getting much higher primary productivity. That's the phytoplankton, and then the trends are given here in tables as well. Okay, so that's happening. Now I guess we'll talk about tundra greenness next. So the productivity on the tundra, right? As the tundra thaws out, there's more water, it's warmer, shrubs start growing, then small bushes and then trees, and then you get an entire forest appearing, very, very quickly. We're getting a greening of the Arctic as the warming occurs. And you can see, some examples here of the greening of the Arctic region. The tundra vegetation's increasing. This is the NDVI, which is a unit to measure the amount of greenness. And you can see Eurasia, circumarctic. These are different types of data satellites that are remote sensing this data. MODIS, Landsat, different satellites recording different NDVIs, and there's images here. So we're getting a greening on the tundra all around the Arctic region. This is a couple of the different data sets. And this is another one here showing all of the greening here in these regions. Yeah, so we're seeing that. Glaciers and ice caps outside Greenland. I'm going to go quicker. I'm going to skip some of these sections because I'm going longer than I want for this video. But you can see the glaciers and ice outside of well, this is covering Greenland too, but mostly it's focusing on outside of Greenland, and you can see the reductions. So this is Alaska. So this is cumulative thickness change in meters, water equivalent. And you can see, look at Iceland drop off a cliff here. This is Arctic Canada green, the Arctic Scandinavia here. This guy here is Alaska. So Alaska is the purple curve here, which is dropping very significantly. The data goes back to about 1940 or so. Cumulative mass anomaly from the different regions as well over time. And then the societal impacts, less ice, less water storage. Atlantification of the Arctic Ocean, I've already talked about that. So atlantification, an influx of anomalous water properties and biota from lower latitudes. So the Atlantic water is impinging deep into the central Arctic Ocean. And it's weakening the Arctic Ocean stratification, so there's more heat transfer to the surface. So we're less and less sea ice. The rapid Atlantification is changing the Arctic. So basically, so you can see Atlantic water here. These are the different currents, the transpolar drift, the different gyres. And you can see, as there's more and more water coming in, then there's less and less ice. So here's, this is sea ice extent, October 2002. Here we are in 2021, and you got Pacific water forcing through the strait here, and taking out this sea ice here. You've got the Atlantic water attacking the edges of the ice pack, and then this is melting up here. So you can get, this is different, this is the rates of some of the currents. Faster is red, slower is blue, average current speeds, and so on in different regions. So you can see, and there's changes in the halocline, right? So we're getting a shallowing of the halocline. It's losing stability, so the more of the water from below that can be warmer is coming up, and it's changing the nature of the water column, and it's ensuring the water is warmer, so there's less sea ice. And of course, warmer water, more evaporation, that leads to the increases in the snow cover extent in the winter region. So there's all of these feedbacks happening. So here, this is some of so we got the ice here. We've got warm, salty Atlantic water coming into the Arctic. We've got the ocean heat moving upwards, and here we have a strong halocline. So we've got salty, dense water here. We've got fresher water here. We've got warm water at the top and warm water down below. And that warm water is pushing upwards, and it's breaking apart the halocline, the stratification. So there's more and more mixing, more and more heat coming up, more and more melting of the sea ice. So you can see lots of sea ice and much less sea ice here. Okay, so those are, and the nutrients are that were here before now are coming up closer to the surface, and with the light coming through, the phytoplankton are growing like crazy. Okay, just a couple more sections. The warming waters and borealization. This is talking about I thought this was the forest, but it's talking about the oceans, the borealization of the oceans. We're getting more and more species in the oceans that are less Arctic species and more lower latitude species. We're getting borealization of the seafloor ecosystems. Some southern species are going farther and farther north as things warm. In the mid-water, same sort of thing, and the top water as well. So we're getting all of these different features. They look at different features and different properties of the water column and the chlorophyll and so on, different species and where they're heading as they head further and further north. Okay, so that's all covered. And then there's a study on St. Paul Island, okay, which is right out in the middle here. There's Alaska right here. This is the archipelago. So we're talking about this island right up in here. 300 to 400 people or so on this island. There's an airstrip somewhere over here, airport right here. So they're doing lots of studies on this. So they were looking at, this is where many of the First Nations people are sentinels or so-called guardians, or doing observations in this region. They monitor coastal erosion. Here they're looking at, they're doing surveys on the northern fur seal rookeries, where the seals are, they come along the coast, and there's far fewer seals now than there was previously. We're talking about, maybe a few decades ago, 300,000 seals coming ashore, and now it's like 100,000 coming ashore. Numbers are way, way down. And then there's a whole article on the rusting rivers. So I'll just show you quickly, what's causing this is the permafrost is thawing. So we're getting the rust gets in the rivers. So what's happening there? Well, this is the redness index. Suddenly, this is 2015, 2020. Look, it shot up here just in the last, say, 5-10 years. In another region, gain way, way up. So these are 3 specific rivers that are monitored, becoming much redder. Basically, the pH drops off a cliff. This is unimpaired water, pH about 8. And then it's about 7.5 when it starts getting red and impaired. And then it drops off, when there's a seep, it drops off to like 2.5 pH. Very acidic. Probably dissolve your spoons in there. This is sulfates going way, way up. And this is the metals. The metal content goes way, way up. It's not just iron. There's aluminum, manganese, zinc, copper, and nickel. And this is what's happening. So the pyrite was underneath here. The active layer was above. As the active layer gets deeper, it exposes the sulfide minerals like pyrite. The water comes through that fills up the river, and it brings up all the metals from pyrite. The iron oxide turns things red. So the water quality is severely degraded. Of course, think of the biological implications. So these rusting rivers are highlighted in this report. And then they talk about the gaps of their knowledge in the Arctic and so on. Anyway, I've gone a lot longer than I wanted to. Thank you if you've lasted the whole time with me. Please consider going to paulbeckwith.net and donating to PayPal, or you can go to a GoFundMe, or I'm on Patreon. And please share this video widely in your social media networks. I'm just trying to educate people on what's happening with climate change. So thanks for listening, and bye for now.